Hi, my name is Patrick Trunowski, and I am the team captain of MCC's drone design team. As a sophomore, this is my second year on this team. As team captain, I'm responsible for conducting all team meetings and overseeing sub-team activity. On the flight line, I will ensure that the mission demonstration is completed safely and effectively.
Hi, my name is Grayson Shuddick, and I'm the electrical sub-team lead, as well as the safety pilot for the team. I'm currently a sophomore at MCC, and I've been on the design team for 3 years. As electrical sub-team lead, I was responsible for directly overseeing the development of all electrical systems on the UAS. I also acted as the safety pilot for all UAS test flights. On the flight line, I'll be in charge of the safe operation of the UAS.
Hi, I'm Brandon Reiner, and I am a member of the mechanical team. I am a sophomore at MCC and have been part of this team for 6 months. During the year, I was responsible for creating the payload delivery system and assisted in the design and creation of the UGV. On the flight line, I will be ensuring the air delivery system is properly configured and that all delivery systems are functioning.
Hi, I'm Peter Owens. I am a member of the mechanical team. I am a freshman at MCC and I have 6 months of experience on the team. During development, I helped design and implement the image system. On the flight line, I will be safety manager and will ensure all pre-flight checklists are complete before takeoff.
Hi, I'm Logan Hampton, and I am on the mechanical team. I am a freshman at MCC and have been working on the team for 6 months. On the team, I was charged with creating the release system for the payload delivery. On the flight line, I will be operating the team's manual ODLC system.
My name is Justin Payne, and I'm part of the mechanical team. I'm a freshman at MCC and have been working on the team for 1 year. During development, I was responsible for creating and overseeing the imaging system. On the flight line, I'll be setting up the imaging system and ensuring that it is fully operational before takeoff.
Hi, I'm Madison Brewer, and I'm the mechanical sub-team lead. I'm a freshman at MCC's engineering program, and I've been working on the team for 2 years. As mechanical sub-team lead, I was responsible for directly overseeing the development of all mechanical systems on the UAS. On the flight line, I will be performing the physical inspection of the airframe to ensure complete mechanical integrity and reliability before takeoff.
My name is Patrick Wilbur, and I am part of the software development team. I'm a sophomore at MCC, and I've been part of the team for 1 year. During development, I was responsible for the development of our ground station web app. On the flight line, I will be in charge of overseeing the setup and operation of the image processing system.
Hi, my name is Yaro Kiefor. I am the software development sub-team lead. I am a sophomore at MCC and I have been working on the team for 2 years. As a programming sub-team lead, I was responsible for directly overseeing the development of all software for the UAS. On the flight line, I will be operating the ground control station to ensure all communications are operating smoothly.
Hi, my name is Brian Donahue, and I am a part of the mechanical sub-team. I am a freshman in MCC's precision machining program and have been a part of the team for 1 year. During development, I was responsible for the design and fabrication of the landing gear and was responsible for the main design of the unmanned ground vehicle. On the flight line, I will be setting up the unmanned ground vehicle and securing it to the airdrop system.
Our UAS, codenamed Big Flying Lilac, or BFL, is a combination of mechanical, electrical, and software-based systems operating together to meet mission requirements. Outlined are the different subsystems on our UAS. For this year's competition, our team chose to create a large HX hybrid frame quadcopter with high-efficiency motors to ensure that we would have enough flight time to complete all mission objectives and land with a power reserve. Our final UAS has a thrust-to-weight ratio of 2.5 to 1 with all systems attached. For our air delivery, our team created a controlled drop system in order to safely lower the unmanned ground vehicle and payload to the ground. This system used a DC motor and a gearbox controlled by an Arduino Uno to lower the vehicle using a high-strength fishing line. For the UGV, our team created a 3-wheeled car that employs differential steering. With this setup, our UGV was able to make precise turns while maintaining a weight within the 48-ounce limit.
On our UAS, there are multiple electrical components needed for proper operation. Our propulsion system uses 4 Tatsu 16 amp-hour batteries, outputting 44 volts with a capacity of 32 amp-hours.
This configuration will allow our drone to have a maximum flight time of 45 minutes. The system also uses 4 100 kV motors using 30-inch propellers. The total thrust output of the propulsion system is 93.4 pounds. We will be using a 2-axis gimbal with a Sony a6000 to take stabilized pictures of ground targets from the UAV. A Ubiquiti Bullet M5 is used on the UAS to communicate images down to the base station. For telemetry data, a pair of RFD900X radios are used to transmit UAS flight data to the base station. Finally, an FrSky transmitter and receiver are used for the safety pilot controls.
This year's Object DLC system is a fine-tuned version of last year's system. Once the images have been received from the aircraft, they are manually classified and submitted to the judge's server using our team's custom web application, codenamed Commander. The objects are also localized based on the drone's heading relative to north and the target's distance from the center of the image.
The obstacle avoidance system uses a ray tracing method processed by an onboard computer to accurately and efficiently plan an avoidance path around obstacles. Additionally, users can manually manipulate the flight path if needed before flight.
For our planned mission demonstration tasks, we will be attempting all tasks except autonomous image submission. We are very confident that our system will capture all waypoints during autonomous flight. We are also very confident that our system will successfully complete a payload drop and an autonomous UGV drive. For our obstacle avoidance system, we are confident that the system will avoid 75% of all obstacles. We will also be attempting manual object DLC and are confident that our system will capture at least 12 of the ground targets. To test the performance of the systems on our UAS, our team conducted strength tests and stress simulations on all structural components. Furthermore, all communication systems were range tested to ensure proper operation at long distances. Before being implemented on our UAS, all software systems were code tested and then tested using our prototype drone. This allowed for debugging before implementation on our main system. Before implementation, all physical systems are prototyped and tested to ensure functionality. Once the system was airborne, our team used the auto-tune feature in Mission Planner to PID tune the autopilot. After the tuning process was complete, several manual speed tests were conducted to determine if our calculations for optimal flying speed matched with actual data. From these tests and our calculations, we determined that the optimal flying speed for autonomous flight was 21 miles per hour. For developmental testing of our autonomous flight system, our team conducted 37 autonomous flights using the Pixhawk 2.1 flight controller and HERE2 GNSS GPS on our competition platform. The autonomous flight system performed well for a large majority of the flights, causing the safety pilot to only take over for 5 of the missions, with the majority of takeovers occurring early in testing. This resulted in an average of 34 seconds of manual flight per autonomous flight. On the Big Flying Lilac platform, 37 autonomous flights were conducted, with 6 being full mission tests, 10 being air delivery drops, 15 being waypoint capture specific, and 6 specifically to test the obstacle avoidance system. This resulted in 193 waypoints being attempted, with 187 being hit within 7 feet.
For each of the 6 obstacle avoidance specific missions that were conducted, each mission contained 2 obstacles. Additionally, the full mission tests included 4 obstacles each. The total number of obstacles tested against was 36, and our UAS had an avoidance success rate of 77.7%. To maximize image quality, multiple camera settings were tested while flying the UAS at the cruise speed of 21 miles per hour and at an altitude of 150 feet. The final settings chosen were 1/400th shutter speed, f4 aperture, and ISO 100. After processing the images, the average resolution of the ground targets was measured at 6,800 square pixels. Since we are not attempting autonomy in the 2019 competition, we instead tested our manual DLC system by feeding images to users who then manually identify and classify ground targets. After initial training, all users were able to operate the manual system with a high success rate.
For our air delivery system, we broke our testing down into 3 phases: drop tests, driving tests, and full payload delivery tests. We first conducted 10 static drops from 60 feet to test the survivability of our payload. Out of the 10 drops, our payload survived all of the landings. We then conducted 10 autonomous driving tests to ensure the accurate waypoint capture of our UGV. Out of the tests, we successfully reached the final destination 9 times with an average distance from the destination of 4 feet. Finally, we conducted 6 full payload delivery missions. Out of the 6, we were able to land the payload with full success and were able to drive to the target destination 5 times. For each of the full mission tests, our payload landed within 10 feet of the drop location. We feel that the tests conducted accurately model the competition conditions and are confident with our air delivery system. Full mission tests were conducted in a fashion that was similar to the 2018 SUAS competition format with the implementation of the UGV airdrop. Each full mission test included 6 waypoints to capture, 1 air delivery drop with an autonomous mission for the UGV, 4 virtual obstacles, and 5 ground targets. 6 full missions were conducted by our team. During full mission tests, our team encountered several flaws in our system. These flaws included an initial failure in the UGV's autonomous capabilities and errors in the consistency of the obstacle avoidance code. To correct the UGV error, the team decided to trigger the auto drive using time instead of the UGV's altitude to eliminate possible false triggers. The obstacle avoidance system will continue to be tweaked to allow for the UAS to more precisely navigate around obstacles. After conducting our 6 full mission tests, our team used the grading rubric provided to grade each of the missions. For our timeline score, we had an average of 28.2 minutes of flight time with 1.3 minutes of post-processing time. At competition, we hope to have a similar flight time, but eliminate any post-processing time. For our autonomous flight, our team scored full points for auto flight and waypoint capture. On average, our team scored 93% overall with an average distance from waypoints of 6.8 feet. We expect similar results at competition. For our obstacle avoidance, our team was able to avoid an average of 3 obstacles per full mission for an average score of 75%. We hope to achieve similar results at competition. During tests, the team was able to effectively identify most of the objects and classify their characteristics. Our average geolocation error across all tests was 21.5 feet. Our average score was 61.2%, which is similar to our expected score at competition. For our air delivery, our team was able to accurately drop the payload within 5 feet of the target destination on 5 of the 6 drops. Furthermore, our UGV successfully reached its final destination 5 times within the waypoint's 10-foot range. We hope to achieve full points for air delivery at competition. We found that our average score across all mission tests was 76.68%. Based on the data collected from this year's full mission tests, our team estimates that our 2019 competition score percentage will be 77%. Our team is confident in our final design of Big Flying Lilac. We hope to represent our university at competition and perform well in the mission demonstration.